We're continuing with our independence and probability. This example, an electrical system consists of four components. A and B are in series with two parallel components, C and D, as shown. The system will function if in each parallel subsystem at least one component works, and in each series subsystem all components must work. And it's asking find the probability that system is working. Assume all components operates independently. Looking at this picture, for this picture to work, basically this subsystem needs to work, and that, and this one. So A must work, and B must work, and C or D must work. So the event that this is working is just event that A works, B works, and C union D works. Now I want to find the probability of that. But before that, let's see if I can make this into something that I can use the independence directly. So I see that A intersect B is intersected with a union. I'm planning to distribute that using the distribution property of sets. So what do I get? I get A intersect B intersect C, and then I get A intersect B intersect D. And the union comes in the middle. So now let's try to find the probability. Probability of A intersect B intersect C is equal to probability of A times probability of B times probability of C. And that is 0.9 to power 2 times 0.8. This also is equal to probability of A times probability of B times probability of D, which by independence is the same thing as the probability of the intersections. Why did I do that? Because now I can say probability of the system working, which is the union of probability of this intersection and this intersection, is probability of the first intersection plus the probability of the second intersection minus the probability of intersection of the two intersections, which if you look at this carefully, it's going to be the probability of A intersect B intersect C intersect D. The first two are 2 times 0.9 to power 2 times 0.8. The last one is 0.9 to power 2 times 0.8 to power 2 by independence. And if you compute this, you arrive at 0.7776. So the probability of the system working is that much. Now let's do the second part of the problem. This is the probability that component C is not working given that the system is working. So it's probability of C prime given W, which is probability of C prime intersection W over probability of W. So let's see remind ourselves what C prime or C complement intersect W was. This is C complement, and W was A intersect B intersect C union D. Because of the commutative property of intersection, I can switch and have A intersect B first, then intersect it with C intersect C complement intersect C union D. So the first one stays, but that actually can be distributed. Again, the distributive property of those set operations. So it would be C complement intersect C union C complement intersect D. So A intersect B. This part is just empty set. Empty set union anything is going to be that thing. Intersect. So C complement intersect D. So now all of these intersection, if I want to find probability of C complement intersect W, I have to multiply all of these. Probability of A times probability of B times probability of C prime times probability of D. And the first two are 0.9. So to power 2, probability of C prime is 1 minus 0.8, which makes 0.2. Probability of D is 0.8. Now let's go back here and compute this. I know the denominator is 0.7776. And so the numerator now is 0.9 to power 2 times 0.2 times 0.8. And that approximates to 0.1667.